With this idea of increasing and decreasing behind us, we can move to the first derivative test. And this is really the answer to what we began back in 4.1 when we first started talking about local maxes and mins. Finally, we're going to be able to identify them, not just the possibilities, the possible local maxes and mins. We're going to be able to figure out what is a local max, what is a local min, and perhaps if there's any critical numbers that are neither a max or min, we can identify that as well. Okay, the first derivative test, it's a big deal. It's got this big, powerful title. And what's it a test for? To find where the local maxes and mins occur. So what are the steps to this test? Step number 1, to find the intervals of increasing and decreasing. Well, that's a whole test in itself. Okay, it's all building, sure. Once we have the intervals of increasing and decreasing, then it will be, there's really not a whole lot more to it. It will be very easy to identify each critical that we marked on that domain line. It'll be easy to identify them as the x-coordinate of a local max, a local min, or neither. The truth is, the first derivative test just takes a very small step beyond finding the intervals of increasing and decreasing. That takes the vast majority of the time. Once you have that, then the answer to what's a local max, what's a local min, and what's neither is just right there staring at you. So here's what we're going to do. We're going to look back at that previous example and just kind of go that next little step. And then we're going to do a whole new one, a more difficult one, all the way through. Oh, there's step 3. I thought we were done. If you recall, local maxes and mins, you need the entire point, right? So we know the x-coordinate from step 2. We'll need to find the y values of the local maxes and mins, and then we'll know the full ordered pair. Okay, we definitely got to mention that. Okay, great. Let's look back at that previous example, and we will identify the maxes and mins. So f of x equals 2x to the third plus 3x squared minus 12x. Okay, so pretend we go through all of the steps for the increasing, decreasing test. We arrived at this domain line with these criticals and those positive and negatives indicating where it's increasing and where it's decreasing, right? Okay, so once we have all this out with the pluses and minuses, then we can go to step 2, identify the criticals. Okay, so these are the criticals, right? -2 and 1. We can immediately identify them as a max, a min, or neither. How can we do that? Okay, so maybe looking at -2. What's happening on either side? So the function was increasing, then it hit -2, and then it started decreasing. Well, doesn't that mean that -2 is a max? It was increasing, it hit -2, then it started decreasing. It was maximized. That's like the top of the hill at -2. So this is a local max. And the opposite for the 1, the function was decreasing, then started increasing. So it's decreasing, it hits 1, and then starts going back up. So that must be a local min. So just like that, boom. Going up, going down, that's a max. Going down, going up, that's a min. And we're not quite done. There is some number crunching. We need to find the y coordinates. These are the x coordinates. We need to find their y coordinates. So what are we going to do? How do you find a y coordinate? You take the value, you plug it back into the original function. So we're going to do that for both of our critical numbers here. So plugging, what did I do there? My mistake. So plugging -2 in right there to the original function, you get 20. And the 1, plugging 1 into the original function would be 2 plus 3 minus 12 is -7. And now we can answer this. All right. At negative 220, there's a local max. At 1,7, there's a local min. We got it. We have no idea what the graph looks like otherwise. Well, we know where it's increasing and decreasing, and we know exactly where these local max and min occur. That's actually pretty good for not knowing, not having a picture of that graph. We figured out quite a bit. Okay, let's try a brand new one all the way from the top. Here it is. Use the first derivative test to find all local maxes and mins. F of x equals x times the quantity x minus 4 to the third. Okay. So, again, these are not short problems. When you see this, any application, these problems are not just, one or two steps, right? So we need a derivative, right? We need to find the critical numbers. Hey, what rule or rules are in effect for the derivative here? And hopefully you notice, well, you need the product rule. And then in this second half, we're going to need the chain rule. Okay, let's try it out. There's our derivative. So we got 1 times x minus 4 to the third plus x times 3x minus 4 squared times derivative of the inside is 1. Okay, so I said it in a previous section. Pretty sure it was 4.1. You got to nail these derivatives. You cannot have any mistakes, right? This is the first step in a long problem, and a goof, even a small mistake in the derivative is going to be very, very costly. And it's going to throw off the rest of the problem. A problem that would have maybe progressed pretty smoothly, clean numbers, good factoring, easy to solve, could just turn into a complete nightmare and is unsolvable. And even, obviously, even if you did, you'd be doing all, who knows what could happen. So take your time with the derivative. Don't rush that. Get your derivative right. It is that important. It's maybe only one step, but it is that important. Okay, let's clean this up a little bit. We'll just call it x minus 4 to the third plus 3x, x minus 4 squared. Okay. So we're still trying to find the critical numbers. Looking to find where this thing is increasing and decreasing. So let's set that derivative equal to 0. Slide it up. All right, x minus 4 to the third plus 3x times x minus 4 squared equals 0. Very tempting to just multiply everything out. Don't do it. Don't do it. You might very well get to the answer that way. It's possible, but you're creating so much more work for yourself and so much more potential for error. And this has got a cube, so even if you do multiply it all out, maybe you can factor that, maybe not, when it's all done. Instead, just think, hey, it's equal to 0. I want to factor, right? In the end, even if I multiply it out, my goal is to factor it. It's ready to be factored now. Just do it now. What do these have in common? They have x minus 4 squared in common. Factor that out. Right there. This one still has an x minus 4 to the first. This one has plus 3x. I like to throw these big brackets on to really make it obvious. Factor it right then. Okay, then we can simplify what's inside these big brackets, right? 4x minus 4. And wouldn't you know it, a 4 factors out of that. 4, x minus 4 squared times x minus 1 equals 0. And in just a couple of steps, it's fully factored. We don't have to multiply it all out and then, combine like terms and then try and refactor it just to end up with this same thing. That's what would happen if we did. Okay. I mean, just think about it. What if you multiplied all that out to get back to this factoring? There'd be like some, synthetic division have to go on, some guess and check, right? Rational roots theorem. You can go there if you must, but 1, 2, 3, boom. Okay, so we got a couple of criticals here. X equals 4, x equals 1 from that equation. Let's also consider the other part of the critical numbers when the derivative does not exist. Well, for this derivative, right, essentially that's just a polynomial, right, if you were to multiply it all out. So we're never dividing by 0 or anything, so that's a none. Don't skip this, because the one you skip, it's going to have it, right? A lot of them are going to be none, but still consider it. Okay, so we have these two criticals, 1 and 4. What's next? Think about the domain. What's the domain of the original function? X times x minus 4 to the third. Again, it's negative infinity to infinity, right? We're never dividing by 0. Something that could change your domain line if like natural log is involved. That could change your domain because the domain of natural log is only 0 to infinity. But most of the things we see, it is going to be all real numbers. Okay, so we're going to make that domain line and we're going to mark off our two criticals, 1 and 4. Just make sure they're in the right order. And just like in the other problem, we're going to say, okay, we're going to take one value from each interval and test it into the derivative. What would be a good choice for this first interval? I think 0 would be a fabulous choice. How about this second interval? I'm going to go with 2, although you could go with 3, either one. And out here, just going to keep the number small. I'm going to go with 5. Hey, you don't have to pick the same things I am. But so long as you get one representative from each, and they get plugged in, I'm just going to show you all this. They get plugged in to the derivative to see whether the derivative is positive or negative. Now at this point, since we've gone through an example, about an example and a half, someone is in a class, in my experience, is bound to raise their hand and say, well, how do we know when to plug into the derivative or the original function? Right? Because sometimes we plug into the derivative, sometimes we plug in the original. Well, it depends on what you're looking for. And after practicing these a little bit, it should become obvious when you want to use the derivative and when the original. Because it's not about memorization, right? Maybe memorize the steps to the test. But even that, like, how do I find the test for increasing and decreasing? Like, that should be, after you do it a few times, it should become pretty natural. Like, okay, I need the criticals. Then I got to mark those and I test, right? Like, it should be clear why that's true, and it becomes less about memorization. Same with plugging in. When do I plug into the derivative? When the original? Well, if I'm looking for when it's increasing and decreasing, I plug into the derivative. If I'm looking for the y value of an ordered pair, I plug into the original. So don't memorize this is when I do this and detach it from logic. Like, well, what am I looking for? Right. Okay, so here we're looking for when is it increasing, when is it decreasing? So we're going to take 0. Is this increasing or decreasing? We're going to plug it into the derivative. And that's our derivative from the previous page. So 0 minus 4 to the third plus 3 times 0, 0 minus 4 squared. Okay, all that's 0, and we get negative 64. The fact that it's 64 is no big deal. We don't really care about that. It's negative, right? So we put a big negative sign right there. How about the 2? Well, skipping, the details, that comes out to be 16. That's a positive answer. F prime 5, also 16. That's a positive answer. Okay. Negative answer, positive answer, positive answer. I also get asked, and these are great questions to ask, by the way, or to be thinking. I also get asked, do we need to show all these steps? Can we just write the line and then just fill it in, and do this in a calculator? In this case, I have to ask that you show these steps in your work on a quiz or a test. Don't not write these, So draw the line. You're like, well, I can just grab my calculator. You could, but I need to see that that's what you're doing. So I need to see this work. Maybe you don't necessarily show that middle step there. You just say f prime 0 equals negative 64, blah, 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 boom, blah, blah, boom, boom. Right? That's fine. But I gotta see that you knew to plug into the derivative there, and you did it. Don't just do it in a calculator. Okay. So we've got the intervals of increasing and decreasing. But we're not going to write all that out because that's not what they're asking. But we can tell it's decreasing here, increasing, and increasing. Now that's kind of interesting that it's increasing back to back. We'll do a Desmos at the end of this section. We'll see what this graph is doing. But hey, it's all right. We don't need to know, right? It's decreasing, then it's increasing, then it's increasing. Okay, so what this is all about, we're trying to find the local maxes and mins, right? So what's happening at 1? That's a local min. Because it was decreasing, hit 1, and then started increasing. Okay. So we know that. How about at 4? What's going on there? It's neither. Because it didn't change. It's increasing, and then it hit 4, then it increased again. Turns out it's going to be that like horizontal tangent line, but it's going up, it levels off, then it goes up again, and it never comes back down. So it's not a max or min if you get that doubled up thing happening. Okay. So what are we going to do? All right, we've identified the local min. That's all we've got. So we're going to take the 1, plug it back into the original, and find the y value there. So there you go, f of 1. Now I'm looking for a y value, so I know to plug it into the original. 1 times 1 minus 4 to the third is negative 27. And I've got the answer. All we've got is a local min at the point 1, negative 27. There's no local max. I don't really have to write this. It's implied if I don't say it, but just to be really clear. Okay, let's stop this video here. More to come.